This is Dr. Reed, and welcome to the Reliability Analysis video. In this video, I will cover the following: the concept of reliability, types of reliability, reliability theory, reliability calculation, the interclass correlations in Excel, Jamovi for internal consistency reliability, and I'll end with a summary. The concept of reliability. Reliability tells you how consistently a measure measures something. Reliable scales, surveys, tests, and raters produce, with minimal error, data that is consistent, reproducible, stable, and predictable. Reliability is not assessed directly, but instead estimated from the data collected, then quantified. There are several types of reliability. This list here gives you most of them. Test-retest reliability, intra-rater reliability, inter-rater reliability, internal consistency, parallel forms. Types of reliability. Test-retest, temporal stability of a scale, survey, or test. Quantifies the consistency of results when the same test or survey is administered to the same sample at different times. Test-retest is the reproducibility of a scale, survey, or test from time A to time B. High test-retest reliability indicates that the scale, survey, or test is stable over time. And here's a diagram of that. So you would administer the survey at a certain point in time, then there's a time interval, and then that same survey or test would be administered to the same sample again. Now, to interpret the reliability, most reliability, if not all reliability coefficients, are similar to a correlation. And so they would range from 0 to 1. So the interpretation for the test-retest would be 0.5 would be acceptable but low, to 0.9 or greater, which would be very good, depending on the length of the interval. So with test-retest, there's a time interval between the administration of the two tests or surveys. And so the longer the time interval between time A and time B, the more that reliability coefficient is going to go down, simply because there's just more things that can happen in between the two administrations that could somehow change people's responses on that second administration. So keep that in mind, and that's a judgment call on the researcher's part as to how long that time interval should be. Intra-rater, it's the temporal stability of a rater. Quantifies how consistently the same person rates or assesses the same thing at different times. Similar to test-retest, except you're estimating the reliability of a rater or raters rather than the reliability of a test or survey. So a little diagram for that would be very similar, virtually identical to the test-retest, except you're looking at raters instead of the actual test or survey. So you would have raters rate some type of phenomenon, some kind of type of behavior, and then there would be a time interval, and then the raters would rate the same thing under the same conditions at a different time point. So you have the same raters at both times, here and here. That way we have intra-rater reliability. The interpretation on that one is similar to the test-retest, 0.5 acceptable but low to 0.9 or greater, very good, depending on the length of the interval. Inter-rater. This is agreement between different raters. Quantifies the agreement between two or more raters assessing the same thing. Quantifies the extent to which different raters agree in their assessment decisions and provides evidence that ratings are not influenced by the person conducting the assessment. So a diagram there is we have different raters here rating at some type of behavior, for example, classroom behavior, and each rater has the same checklist for deriving a score for the thing that they're observing, and then your analysis is going to look to see how consistent the raters are between them among themselves. So the interpretation there is roughly 0.4, which would be acceptable but low, up to or greater than 0.9, which would be very good. Internal consistency quantifies the consistency of participant responses across items on a multiple item measure designed to assess a single construct. Generally, when the items on a test or survey are intended to assess the same underlying construct, participant scores on those items should correlate with each other. So for example, if you have a 5-question survey or a 5-item test, what you could do is, and this is just conceptual, it's not necessarily exactly how it would be calculated, but you would correlate all pairs of items, then compute the average of all the correlations. This will give you an index of the internal consistency of the scale, survey, or test. The interpretation there ranges from 0.6, acceptable but low, to 0.9 or greater, very good. Note, the internal consistency values, if they get too high, they go above 0.95, for example, may indicate what I would consider to be useless redundancy among the items or among several of the items. So internal consistency, one of the points is to try to see how much redundancy you have in the items on your scale, test, or survey. But we want them, because all of the items are assessing the same construct, we want them to be somewhat redundant, but yet a tiny bit separate. And if they're too redundant, then it's possible that they're so closely related that it's useful to have those two questions, for example, that are so closely related. So you end up having, you could potentially remove a few questions. So I'm labeling that as useless redundancy among the items. So this one's a little tricky. This is called internal consistency reliability, and it's a little bit different concept than what we've been talking about so far with the different types of reliability. It's different conceptually than test-retest, intra-rater, or inter-rater. Note, high internal consistency reliability does not confirm that the test or survey is measuring the construct or thing it is supposed to measure. This is validity. Instead, high internal consistency reliability reflects strong coherence, or what I would dub as useful redundancy of test questions or survey items. Because remember, the idea here is your test, survey, or scale, you want that to be assessing the same global overall construct. So there needs to be some redundancy amongst the items, but not so much that each item or several pairs of items, for example, are essentially asking exactly the same thing. This is internal consistency reliability. And then the last one is parallel forms, sometimes called equivalence. Quantifies the consistency between two versions of a survey or test designed to measure the same construct, content, or skill. Using reliable parallel forms of a test, for example, can help reduce the risk of testing effects. So one of the things, if you think back to the very first type of reliability that I talked about, the test retest, one of the issues there is that you're giving that same test twice. And so you end up wondering that whether or not the consistency or reliability of that test is just simply due to the fact that people are remembering exactly what they put the first time you administered the test to them. So that's an issue that you have to grapple with when you deal with test retest reliability. And different forms of assessment are more susceptible to that than others. For example, tests that are skill related, maybe a test that the physical education teacher gives, those types of tests are not as susceptible to memory effects, if you will, because they're more skill related than you would have if you gave more of an academic type of test. So parallel forms is useful for tests that are more written in nature, spelling, algebra, etc. And this way you know you have two different forms of a test that basically measure the same concepts, and they're reliable too. Okay, they're highly correlated. So for example, one way to do this would be to randomly split a 50 question test into two 25 question tests, test A and test B. Give test A to all students, and then 1 week later, for example, give test B. So now, because you have different questions that are supposedly asking very similar things, you avoid some of the memory effects from the first administration to the second administration. So you have test A with 25 questions. Then 1 week later, you give test B with the 25 questions. So in theory, these two tests are very, very similar to one another, and they're also highly correlated. And you also can feel more confident that they're related because the two tests are measuring the same construct or the same skill, the same types of things, rather than the notion that people just remembered what they put the first time you gave the test on the second administration. So this is a strategy that can be used to develop the reliability of a certain test, certain scale, or even a survey for that matter. Interpretation, 0.6 acceptable but low, up to 0.9 or greater, which would be very good. This is parallel forms. Parallel forms. Let's talk a little bit now about reliability theory. Reliability theory. This will lead us to the general way that reliability is calculated for statistics and research. Reliability theory says that the scores in any data set were obtained with some degree of measurement error from the true scores. This means that the variability or observed differences between scores in your data set, as seen both between subjects and within subjects for repeated assessments, are due to true score variability and error variability. In other words, the total variance, S squared total, in your data set is comprised of true score variance, S squared subscript true, and error variance, S squared subscript error. And so there's the way that can be seen. The total variance is equal to the true variance plus the error variance. And so you can see here that this total variability can be divided up or partitioned, if you will, into these two components. The theory also says that reliability can be defined as the proportion of the total variance that represents the genuine trial-to-trial or question-to-question variability of responses, and therefore can be quantified as reliability, R, would be equal to the true variability in the data set divided by the total variability in the data set. Now we know that S total is equal to true plus error, so you could also say that the reliability would be equal to the true variability divided by the true variability plus the error variability. Since S total, as I mentioned before, since S squared total, the total variability can be partitioned into true and error components, we can use analysis of variance procedures to compute reliability. Reliability calculation. So now I'm just continuing from the prior slide leading up to the calculation part. To compute reliability with ANOVA, we use the row and column variables in the data set to calculate S squared true and S squared error components, or the true variance and the error variance components. However, we only have observed scores, not true scores. So we need to find an appropriate substitute for the true variance that represents the real trial-to-trial or question-to-question variability of subject responses. Because remember, we're after this concept of reliability here. Because reliability can be defined as the trial-to-trial or question-to-question variability of the subjects, the row variable representing between subjects variability, absent error, across trials or questions is the correct substitute for the true variability or the true variance. So the reliability coefficient using ANOVA is called the intraclass correlation coefficient, ICC, and can range from 0, no reliability, all variance in the data set is due to error, to 1, perfect reliability, all variance is true variance. So now I'm going to show you on this second slide for the reliability calculation, I'm going to show you a schematic of how this is done. So sort of putting it all together so you can sort of visually see how this makes sense. So we start out with, there's your data set. So we have this data matrix then, which would be what you would have in Jamovi or Excel or any statistical program. And we can then use these different components to calculate our interclass correlation coefficient. So you can see here, you would have over here, if you look over here on the left, we have subjects, 1, 2, 3, all the way down to however many subjects you have, n. These are listed in this column. And then the next column over, you have your measurements. Measurement number 1, measurement number 2, measurement number 3. These could be your measurements. These could be the questions on your survey. These could be the test items on the test. These values that you see here for the columns then could be a rater that's rating a behavior on 3 different occasions, etc. So what is important here is that you can see that we have rows of data here. I have that kind of label as blue that represent the subject responses across the different measurements. So each row is the subject responses across the different measurements. And then each column represents all the subjects' responses for a particular measurement time or a particular rater, etc. And then if you have this information, then you can get the averages of those. So I have here in blue to correspond with the row variable or subject, we can get, so for this first subject, you could take the average of their responses here and get this average right here, mean for row 1. Then you could have a mean for row 2 and a mean for row 3, etc., all the way down for however many subjects you have. Likewise, we can get the means for the columns. So we have the column means. I have those in red to correspond to the column. So we have mean of column 1, mean of column 2, mean of column 3, all the way over to however many questions or raters that you have, for example, or time periods. So this is how we're going to do this in terms of the ANOVA procedure. You can see that we can come up with these means here. And so these means here represent the 2 different variables. This would be the subject variable here, and this would be the means representing the column variable. Then you also can have a grand mean, which is the mean of the means for the entire data set. So if you took these 3 values here, for example, mean of column 1, mean of column 2, mean of column 3, if you just had 3 time points, and added those up and divided by 3, you would get the grand mean, or the mean of the means for the entire data set. If you did the same thing with the rows, mean of row 1, mean of row 2, and mean of row 3, added those up and divided by 3 in this case, you would get the same value. You would get the grand mean. So this is going to be our setup to compute those variance components that we need to calculate the interclass correlation coefficient to get the reliability. So how is that done? Now we have sort of a map here for how this might be done. So the first thing that the computer will do is, to get this variance, we need the sum of the squared deviations of different components. It sounds complicated, but it's not. So this here stands for, SS stands for the sum of the squared differences. And in most textbooks, they label this the sum of the squared deviations, but I like to use differences because it's a little more concrete. So this would be the sum of the squared differences of the total, sum of the squared differences for the column, sum of the squared differences for the row, and the sum of the squared differences error. So what does that mean? What does that mean? Well, let's take a look at the first one here. And that would be the sum of the squared differences for the total. So what does that mean? Well, if you took the data that you have here, I have that grayed out to correspond with SS total. So all that is that the computer will take each response in your data set, subtract it from the grand mean, and square it. Then just add those values together. If you do that, you get the sum of the squared differences of each score in your data set from the grand mean. That gives you a value. That would represent the total variability in your data set. The sum of the squared differences between each score in the data set from the grand mean. Again, take each score, subtract it from that grand mean down here, and square it. And then add all those values together. This gives me the total variability in the data set. So the total variability will be equal to the column variability plus the row variability plus anything left over, which would be the error variability. So what about that second one? It'd be the SS for the columns, right? So I have that labeled as kind of a red or pink to correspond to the column means. So how do we get that value? Or how does the computer get that value? Exactly like it was done for the SS total, except for we just use the means of the columns. Take the mean of column 1 minus the grand mean, square it. Take the mean of column 2 minus the grand mean, square it. Take the mean of column 3 minus the grand mean, and square it. I have 3 values there. I add them together, and I get the sum of the squared deviations for the column. Easy. Now you're getting the pattern now. What about the rows? I have that in blue, which would be right here. You do exactly the same thing. Take the mean, this value here, the mean of row 1 minus the grand mean, square it. Mean of row 2 minus the grand mean and square it. Mean of row 3 minus the grand mean and square it. Add those up, you get the SS row. Very simple arithmetic, essentially, to kind of look at the variability. And then, so we can get those values, okay? The computer will get those. And then the error, how do you get that? We can just get that from subtraction, And so the SS error would be, once you have the total, the column, and the row, The error is just the total minus the column minus the row. Meaning whatever's left over from the total after we subtract out the column and row is going to be the error. And so for our calculation here, I just went through a review, but for our calculation, we only need a couple of these values. We don't need all of them. We only need the row value and the error value. Those are the only two we need to get our interclass correlation coefficient. Because remember, what we're trying to find is a reasonable substitute for the true variability in terms of the subject responses across the different measurements. Because we're trying to get at the reliability of the responses. So the only thing you have to do next, or the only thing the computer would do then, is take the values that we need and divide those sums of squares values by the appropriate degrees of freedom to get sort of like an average of the sum of the squares. And that's called the mean square. So our formula then for the ICC, the basic formula then will look just like something like this. It will be the mean square for the row, which is our appropriate substitute for our subject variability across the measurements, minus the error. Do that first and then divide that by the row, mean square. But let's clarify that though. So let's remember what the theory said about reliability. So if you look down here, our equation based on the theory says that we have the true variance divided by the true plus error, as mentioned on those previous slides. Well, the numerator that we have in our basic interclass correlation coefficient is exactly that. We're taking our appropriate substitute, which is the mean square for the row, and we're subtracting out the error from that. We're sort of purifying that in order to get our true variability as far as the subjects are concerned in terms of their responses across the trials. So we purify it to get the true. And then in the denominator, according to the theory, is this, as was mentioned on the prior slides, and that is going to be equal to or representative of the MS row, the true plus its existing error. So the basic calculation there is fairly simple. This will give us the reliability for our instrument or our raters, etc., that we're looking for. So the ANOVA procedure, if we find the right components, we can match them up to the theory to calculate the reliability. So what I'm going to do next now is I'm going to move on to taking a look at an Excel data sheet that I have that will calculate different interclass correlation coefficients for different types of reliability that you may want to calculate. And I'm going to give you the procedure for that. So I'm going to pause the video, pull that up, and we'll continue from there. Okay, so here I am in the Excel worksheet for the interclass correlation reliabilities, and I have an example data set over here on the left. And these are values from a physical test that measures leg power in athletes. And I have a method for you to use this if you need it for reliability for your dissertation, for example. So this database here has 13 subjects. You can see 13 people were measured at 3 different times on this same test. And so we want to get the reliability of this test. You can see also too that this worksheet will go up to 5 columns for 5 different raters, for example, or a single rater rating something 5 different times, or 5 different time points, or a survey or test or questionnaire having at least 5 items. And then it goes down to 20. And I can always make that bigger for us too. So how are we going to do this? Well, we're going to use the data analysis tool inside of Excel to obtain the appropriate analysis of variance output. And then from there, as I was showing on the slides, you can compute the interclass correlation coefficients. So how do we do that? So what you're going to need to do is you need to have the data analysis tool installed in Excel. And if you have it there, you would go to the data tab here, and then it should show up over here on the right hand side. So click on data analysis, and it's a tool that has different statistical functions on there. And the one that we're going to use for this purpose is the ANOVA two-factor without replication. Without replication. That's the correct one to use for Excel for our purposes. So you would select that, click OK, and you get a little dialog box that comes up here. I'm going to go back a little bit there and so I can show you how we're going to do it. So this little box comes up, and so it's asking for the input range. So you click in there and then select your data. So you would just go over here and select the data here like I've done. So it shows up here. And then it asks whether or not there are labels in your selection. In this case, it's best not to select the labels. Just select the actual data. And then for the output, I'm going to have you, if you want to use this worksheet, you click in the output range there, and then click cell J2 for the output. So you put your cursor there and click in cell J2 for the output. You click OK and you're going to get the output. So I click OK. The output comes up. And now what we need to do is scroll down because Excel is giving you some summary statistics here first, but we need that ANOVA table. So we're going to get this ANOVA table. It says copy and paste the ANOVA table to cell or at cell A1 on the reliability sheet. So I'm going to scroll down here. There's my ANOVA table. I'm going to copy that like that. So I'll go back up here to copy. And then I have another sheet down below here. It says reliability. So you click on that. And now you're ready to go to cell A1 right there, cell A1, and paste it in there. And once you do that, it's automatically going to calculate the reliabilities for you. So I'm going to hit paste, and the reliabilities are calculated for you. So now you can just focus your attention over in this purple box. And so I put the formulas in there for us. And there are several different types of which you don't need to necessarily pay attention to all of them. So there are 1, 2, 3, 4, 5, 6 different types. But for the different types of reliability that I am covering in this video, I've labeled those for us. So if you are looking to do test, retest, intra-rater, or parallel forms reliability for your data, you would read this reliability coefficient right here. So it would be 0.71 is what it is for those 3 trials for that leg power test. 0.71 is the intra-class correlation coefficient for that, indicating that it's pretty good reliability there from trial to trial. If you're interested in inter-rater reliability, you would use this one here. And that one in this case comes out basically the same for this particular data set. And it comes out at 0.71. If you are interested in using this worksheet for internal consistency, then this one here in this row is equivalent to Cronbach's alpha for the internal consistency. And in this case, we have a value of 0.88, which is right where you want it to be. Very good. Not too high, but pretty high and not low. So that'll give you the coefficients that you want, minus the confidence intervals, which I haven't put in there yet, but that's for another time. The other thing that you can do, or another supplementary statistic that you can get with your reliability analysis, is the precision of your data. The precision. In this case, it's the precision of any score. And so there are some other definitions of reliability, and one of them has to do with precision. Okay? And so what I've come up with, it's the standard error of the mean here with a 95% confidence interval around it. So essentially, if you go down below here to the italicized description, for this data set that we just analyzed, you can be 95% confident that any participant's true score that you have in your data set that you can see will be in the interval between their observed score, the one that you see, plus or minus the 95% Mo value that's up in this box right here, 63.73. So in other words, I can go to the previous sheet there and pick any person's score, one data point, take that value and add 63.73 to it and subtract 63.73 from it. And that I will be 95% confident that that person's true score is in that interval. So the narrower the interval, of course, the more precise the measurement, and typically the higher the reliability. So that's that Excel worksheet. And now I'm going to pause the video and go to Jamovi, and we'll talk a little bit more specifically about the internal consistency reliability, which is what Dr. So wants to make sure that you do if you're going to do a survey for your dissertation. Now I'm in Jamovi, and I have that same data set that I used for the Excel intra-class correlation coefficient analysis. But in this case, Jamovi allows you to do reliability analysis also. So the way that is done is, there you can see I have the same scores that I had in Excel. And for reliability in Jamovi, you want to go to Factor up here. Factor. Click on that, and you can see you have reliability analysis. So you click on that, and as usual, you just bring over the variables that you want from the left box to the right analysis box. And you can see here down below, after you do that, you have your choices of Cronbach's alpha, and then the alternative called McDonald's Omega, which is the one that I would recommend, and I'll explain that in a second. The other thing you can do is you could just do both. So I'm going to first of all bring those trials over there for the leg power test. And then all you have to do is just click on the McDonald's W in addition to Cronbach's, and you basically get your response there. And so you have the two. So Dr. So is going to recommend that you do Cronbach's Alpha for the internal consistency reliability, which is a typical reliability that you're going to want if you administer a survey. The reason why is because you need some type of reliability, right? But you're probably not going to want to give the survey twice. You usually just give the survey once. And so that would be the appropriate reliability too, is where you're going to administer this thing one time. And so you can't get test retest because you only administered it once. So the internal consistency is going to be the one that you're going to want. And we have a choice between Cronbach's Alpha and McDonald's W. I'm going to recommend that you would use McDonald's W in the vast majority of cases, or McDonald's Omega. And because it is going to be more accurate than Cronbach's, because Cronbach's Alpha has a number of assumptions that have to be met, which are oftentimes difficult to meet with real world data, that if they're not met, Cronbach's Alpha will not be as accurate as McDonald's W. And the particular assumption that Cronbach's Alpha has to meet is the assumption that all of the items in your survey, for example, so let's say you have 15 questions. When you calculate the reliability, you get a single number. In this case, we see we have 0.88, and that assumption says that all of the questions contribute equally to the calculation of the final coefficient. The problem is, in real life, that rarely happens. Some questions are more important than others, etc. McDonald's Omega does not require that assumption. And so what's nice there is it's going to be more accurate, because if that assumption is not tenable with your data, then Cronbach's is not going to be as accurate. And so you can see in this case, we only have 3 items, right? And so typically you would have more for a questionnaire. They're roughly equivalent here. We have 0.88, right, rounded to 2 spots, and 0.89. So you could report both, and then if they're markedly different, you would go with McDonald's Omega. But I would recommend that you would go with McDonald's Omega, particularly if they're different from each other, because we would be pretty confident under that scenario that Cronbach's would not be as accurate. So that's how you can easily obtain your internal consistency reliability with Jamovi. So now I'll pause for a second and go back to the PowerPoint slides for the summary. So let's now summarize the reliability analysis video. So reliability tells you how consistently a method measures something. The test retest quantifies consistency when the same test or survey is administered to the same sample at different times, noting that that time interval is an important consideration. Intra-rater quantifies how consistently the same person rates or assesses the same thing at different times. Inter-rater quantifies the agreement between two or more raters assessing the same thing. Internal consistency quantifies the correlations between items on a survey test or scale intended to assess a single construct. McDonald's Omega is less likely to produce misleading reliability estimates when the data does not meet the strict assumptions of Cronbach's alpha. Parallel forms quantifies how well two versions of a survey or test covering the same material correlate with each other. Finally, the reliability coefficient with ANOVA is called the intra-class correlation coefficient, ICC, and can range from 0 to 1 perfect reliability. So that takes care of the final analysis video for the semester. There's a 5-point quiz, as usual, for the video. If you have any questions or any issues regarding this one, please send me an email. Thanks for watching.